Good afternoon. First of all, I would like to thank the organizers for inviting me, to give me an opportunity to give my lecture. And my lecture is focused on palladium-based catalysts for sustainable chemical processes. So I will quickly introduce you something about sustainable chemical processes, the role of the catalyst, palladium applications, innovations, and nanocatalysis. Some case studies, further future directions, and finally some market trends. So what about the sustainability? Well, the chemical industry contributes roughly about 20% of the global carbon dioxide emission and also consumes a huge amount of energy. So that's on the one hand. On the other hand, we know that the policies becomes more and more stricter, and we're also aiming at zero emissions. So sustainability actually is not an option anymore, it's really a must. So, and what can we do for sustainability? Or to reach that? Well, we can, of course, reduce the emissions of carbon dioxide. We can use the carbon dioxide and convert it into chemicals. That's another option. We can use alternative energy, such as wind and solar energy. We can recycle. We can, of course, look to the United Nations SDGs. So try to get all these 17 SDGs from the United Nations. So there are plenty of things we can do to become more and more sustainable. And in this aspect, a nice example is the combination or the cooperation between BASF, SABIC and Linde, where they put hands together to demonstrate the first fully electrical heated steam cracking furnace using renewable electricity. And due to this, they could reduce the amount of carbon dioxide emission with at least 90%. So this is really a good example. So what's the path to lower the emission and for sustainable growth? Well, for instance, in the US, the chemical industry consumes about 10% of the fuel. And also they produce about 4% of the carbon dioxide emissions. So if nothing is done, by 2050 the carbon dioxide emission in the US will be doubled. But they did some actions and there was some reduction, but on the other hand there is more production. So if you make the final balance, they end up with roughly 9% more carbon dioxide emissions. So there's still a lot of space to do something. There are a lot of opportunities. And according to Deloitte, there are about 15 solutions, of which 4 can be implemented in the next decade. The rest, 11, are still in initial phase or in between somewhere. So there's still a lot of development necessary. And about 90% of the US companies, they produce carbon dioxide or emissions directly by using fossil fuel or indirectly by buying electricity or steam, something like that. So there is still a lot of space to further improve and to grow in sustainability. And if you look to all of this together, this is actually a multi-trillion-dollar business. So what's the role in this sustainable chemistry? The role of the catalyst. So the catalyst actually can reduce the temperature of the reaction. It can also have a higher yield and higher conversions. That means you will have less side products. Your product will be purer. And actually you could say that doing more with less, cleaner, faster and greener. And you all know the three-way catalytic converter, which is at the bottom of your car, unless you have an electric vehicle. But if you have a combustion engine, you will have this catalyst. And in this catalyst, we have a certain amount of PGMs. And these PGMs convert the toxic NOx and CO into carbon dioxide and nitrogen gases, which are not toxic for humans. So I told you about those 15 solutions that Deloitte suggested. Here you can see them on the right side. The 4 solutions which will be implemented in the next decade is related to hydrogen, related to carbon capture and renewables. And the rest is in the initial phase or somewhere in between. But important for all of this, you need palladium. So palladium is actually metal of the moment. So what are the catalysts and their advantages? Well, this is a little bit of chemistry, sorry for that, but catalysts are mainly based on transition metals, and transition metals are situated in the middle of the periodic system. And in this block of transition metals, you have the right red rectangle. These are the PGM metals. So because they have d orbitals, so not fully filled with electrons, you can play with them. They can take electrons up, they can give electrons away. So actually they can easily coordinate with ligands, with substrates, they can perform a redox reaction. And in this respect, palladium stands out for its versatility, activity and scalability, and organic transformations. And organic transformations, some key organic transformations are, for instance, the carbon-carbon coupling. This is really important, especially for pharmaceuticals, some agrochemicals, and even for some bulk chemicals. So next to that, palladium is also very precious for hydrogenations, selective hydrogenations and bulk hydrogenations. You can make the catalyst homogeneous, heterogeneous, but I will come back to that later. And also palladium is quite tolerant against functional groups. So what are the key applications of palladium catalyst in industry? Well, it has been mentioned several times already, but palladium, roughly about 80%, is used for this three-way catalytic converter. Then you have a little bit for investment and a little bit for jewelry, and the remaining part is mainly used in industry. Which kind of industry? The chemical industry, you have dentistry, you have the hydrogen industry, which is coming up more and more. And in the chemical industry, we are focusing on pharmaceuticals, agrochemicals, even polymers, fine chemicals, and bulk chemicals. Just to show you, because I'm a professor, I have to show some chemistry, to show you some important reactions using palladium. We call them, they are all coupling reactions. And one is the Suzuki-Miori coupling reaction on the right side on the top. The other one is a Heck reaction on the left side, and then we have the Sora-Hashira coupling, and also the Buchwald-Hartwig amination. So these are actually key reactions for many fine chemicals as well as bulk chemicals. And for this we need really palladium. So just to prove that it's not nonsense what I'm telling you, there are examples of pharmaceuticals. We have, for instance, the Valsartan, which is produced by Novartis and is a high blood pressure medicine to reduce the high blood pressure. We also have, for instance, sitagliptin, which is a medicine which is used to cure diabetic diseases and is produced by Merck. And there are plenty of others. So actually the palladium is key for all this kind of pharmaceuticals as well as agrochemicals. So coupling is indispensable in modern drug synthesis. So what about innovations in the palladium catalyst for sustainability? Well, some chemistry again. Normally, if you use a heterogeneous catalyst, you take a palladium salt, for instance, you will impregnate that on the support, silica, alumina, or whatever, and you will calcine and you have microcrystals. And from this microcrystal, actually only a fraction, maybe 1%, if it's very good, will be active. So actually a lot of your palladium is not used. So if you go in the direction of nano, so from micro to nano, you will have actually an increased surface area of the palladium nanoparticle, and that means you have more active sites. More active sites means higher conversion, higher yields. So the nanoparticles can have certain sizes, let's say between 2 and 5 nanometers, and they can also have certain shapes. The morphology is important in catalysis. But sometimes you don't need to worry about the morphology, a nice shape, cubic or hexagonal. Sometimes amorphous is also fine. It depends on the reaction and on the conditions. So how you can design that? Well, as I said, you need a support for heterogeneous catalyst, of course. You need a support, could be alumina, silica, carbon. More trendy and newer supports are metallic metal-organic frameworks or porous organic POPs, polymers, the POPs. And why? Because, for instance, these last category, the POPs, they can be semiconductive. And if you put palladium nanoparticles on a semiconductor, you create a mod Schottky interface, and you can suck all the electrons to that palladium nanoparticle, and there you have excellent catalytic performance. So you see a structure, actually an NMR spectrum of this kind of POP, and next to that you see nanoparticles of roughly about 5 nanometers. And on the left side you see another way how you can make heterogeneous catalyst. The first way was supporting nanoparticles supported on the support, or the second way is you can encapsulate nanoparticles. And here we developed a method in which you take all the ingredients to prepare a MOF, as well as the palladium source, you mix everything and you spray dry. And due to that you have a catalyst, palladium nanoparticles, which are immediately encapsulated in a MOF. So here you can see tomography at the bottom, tomography of a MOF particle, and the white arrows point to the palladium nanoparticles. So there are benefits if you go to nanoscale palladium particles. As I said, you have a higher surface area, you have more active sites available, so you will get higher conversion. But actually there is even more. You will also gain in selectivity. That means less side products. So on the left side you have an example of the blue particle, nanoparticle, which is used for the hydrogenation of butadiene. And at high conversions you can see that the selectivity starts to drop, maybe up to 60 or 70%. And on the very left side you see a single atom catalyst. That's what we want to have actually. This single atom catalyst shows the same conversion, but it keeps the selectivity at 100%. That means with this kind of catalyst you don't have any side products anymore. You finish your production, you can use your product immediately, no purification, no nothing. So a case study where we use palladium is glycolic acid production. And why glycolic acid? Because glycolic acid is actually an important chemical platform, and it is used in cosmetics, pharmaceuticals, and other intermediates for pharmaceutical compounds. You can use it to make biodegradable polymers, for instance, the combination of PLA and PGA. This copolymer can be used to make bone screws. So if somebody's bone is broken, they put some screws inside. So these are the screws they use based on this polymer. You can also use it for sutures. So if you have a wound, to sew the wound, they use this kind of wires. Also, glycolic acids are used to produce certain fungicides. It can be used in the chemical chemistry for electroplating, and also some bulk chemicals. So there are quite a lot of opportunities with glycolic acid. So how do they make glycolic acid? Well, traditionally they use the organic chemistry. And in using organic chemistry, they have quite harsh conditions. They have a lot of byproducts, so a lot of after purification steps. They have low selectivity. And if you use palladium, you can avoid all of this. And on the left side, you can see on top that carbonylation is another way to produce glycolic acid. But this happens to be in 2 steps. So for this reaction, they use a heterogeneous palladium catalyst, and the reaction happens in 2 steps. Although, for instance, Monsanto uses a rhodium catalyst, homogeneous, for this reaction, and I think Cativa uses an iridium homogeneous catalyst. So they have problems to purify the product after the reaction because of the homogeneous catalyst, and also they use some corrosive halides. The solution actually is the use of a palladium catalyst, actually a palladium gold catalyst, an alloy. And with this palladium alloy catalyst, you can oxidize ethylene glycol, which is derived from biomass, so this is a sustainable product. And if you oxidize this with normal oxygen, you immediately get your glycolic acid. So this is really a green, sustainable process. And moreover, the yields are 93, 94%. The reaction conditions are very mild, 60 degrees, so that's very convenient. You have a very high selectivity, 98%. The waste is actually neglectable, and the catalyst is reusable. So this is really a very interesting catalyst. I will compare the palladium with platina for certain reactions I did. That's not in general, but just to give you an idea. So palladium shows a higher activity compared to platina. You can have the same activity with platina, but you will have to use more. So you have to think about the cost and so on. Also, palladium, the nanoparticles tend to be smaller than platina nanoparticles, and also they are much more thermal stable, meaning they don't migrate or aggregate with each other. So you keep your nanoparticles. So you need actually a lower loading for your nanoparticles if you use palladium, and the waste is minimal. Also, palladium is easier to make alloys compared to platina. So you can create a lot of new properties actually if you start to alloy your palladium. And I guess these are the most important aspects I highlighted for the comparison between palladium and platina. Okay, so what are the future directions and challenges? Well, if you have a heterogeneous catalyst, you always can have some issues which are depicted on the right top figure. So you can have carbon decomposition, you can have leaching, you can have agglomeration, or you can have poisoning. But if you use the palladium catalyst like we use for our glycolic acid, well, we don't have the carbon deposition because our temperature is very low, 60 degrees. If you look to leaching, we can neglect the leaching because it's a very stable catalyst. If you look to agglomeration, the nanoparticles don't agglomerate. This is one of the suitable properties of the palladium nanoparticles. And if you think of poisoning, well, poisoning is actually coming from your substrate. So if you purify your substrate, you avoid poisoning and the problem is solved. So below that figure, I showed you a palladium pop photocatalytic system. So actually it's an instant reaction. You put on the light, it reacts immediately, and we recycle the catalyst. And I guess after 6 or 7 times reusing this catalyst, the conversion starts to drop a little bit. But if you wash this catalyst with simple ethanol, you can reuse the catalyst and you have again 100% conversion. So that also means we don't have leaching. So this is a very convenient way, and palladium is quite interesting to perform all kinds of catalytic reactions. And another issue is the conversion. So the limitation could be the conversion, but as I mentioned, if you go from microcrystals to nanoparticles, you increase the active surface area, you gain conversion, you gain yield. If you go further to single atom catalyst, you even gain selectivity. So not only conversion, but also selectivity. So if you want to avoid these kind of issues about low conversion and a lot of waste, you have to go to single atom catalyst. So emerging technologies, especially with palladium, is electrochemical systems for all kinds of reactions related to water splitting, water oxidation, and so on. Also photocatalytic reactions. It's very convenient to, let's say, put on the light and your Suzuki coupling immediately happens. You turn off the light, it's finished. You have a clean product. You just have to get rid of the solvent. But of course, other emerging technologies is the use of artificial intelligence. So we have so many data available. We have to collect these data, put it in a model, machine learning. From this machine learning, we can get some predictions. These predictions we will have to put in the computer to see if it's suitable. We have to make this loop several times, and at the end, we have excellent new catalyst which we can make in the lab. So what about the market trends and demand regarding palladium? Well, it's expected or projected that the annual growth rate will be 5% or more, and especially in the Asian region, there will be a lot of use of palladium. We have seen today and yesterday that actually China is one of the main consumers of these PGM metals, and the main drivers will be the pharmaceutical industry and the electronic sector. So increasing demand for palladium catalysts will be for instance, automotive, although combustion engines will decrease, that will not be for tomorrow, so still a few decades we will use combustion engines. Also for aerospace, palladium is very interesting because of its unique properties. In the chemical production, I'm sure that palladium will be used more and more for different kinds of reactions and even replace certain other PGM metals. And for, of course, the green technology related to fuel cells, we have seen several lectures pointing out that fuel cells will become more and more popular, and also for wastewater treatment. We should not forget wastewater treatment. Palladium also plays a crucial role in that. So, of course, if you use all these PGM metals, and I'm focusing on palladium, recycling is also a must, especially if you want to be more and more sustainable, and if you want to stabilize the supply chain, you have to think about that. And in global, for instance, global use of palladium, we can see that in 2022, roughly about 50% is recycled, 50% is new. And if you look to which areas recycling happens, it's mainly around 32% from the automobile industry, 73% of the electronic industry, and the remaining part is from jewelry. So this is the recycling. And finally, I want to just bring to your attention some new item. It's the Palladium Toolbox. We developed the Palladium Toolbox for the area of catalysis, an area of hydrogen tech and electronics. So each box has specific, in case of catalysis, specific heterogeneous catalysts, some precursors, some supports. You can prepare your own catalyst if you want. Similar idea for the hydrogen tech and for the electronics. And finally, I would like to thank you for your attention.